Have you ever wondered if there's a shortcut through space and time? Imagine traveling to a distant galaxy in seconds, or even glimpsing another universe. This is the mind-bending concept of wormholes, mysterious tunnels that could reshape our understanding of reality. For millennia, humanity has gazed at the stars, seeing them as distant, unreachable points of light, separated by an impassable void. But what if the universe isn't as vast and empty as it appears? What if the fabric of reality itself holds secret passages, shortcuts through the cosmic expanse? The key to unlocking this mind-bending possibility lies in the work of one of the 20th century's greatest minds. Albert Einstein, with his theory of general relativity, didn't just describe gravity as a force. He revealed it as a consequence of mass and energy warping the very structure of space-time. He taught us that space is not a static stage, but a dynamic, flexible fabric that can be bent, stretched, and twisted. It was within the complex mathematics of his own equations that a startling implication emerged. In 1935, working alongside his colleague Nathan Rosen, Einstein discovered a theoretical solution that described a bridge connecting two different points in spacetime. This structure, formerly known as an Einstein-Rosen bridge, is what we now popularly call a wormhole. It wasn't a deliberate search for a cosmic shortcut, but an unexpected and profound consequence of their exploration into the nature of gravity. To grasp this concept, imagine the universe is a vast, flat sheet of paper. A journey from a point on one side to a point on the other would be long and arduous. But what if you could bend the fabric of space-time itself? If you fold the paper, bringing those two distant points close together, you haven't changed their positions on the paper, but you've dramatically altered the distance between them in three-dimensional space. Now, if you could punch a tunnel directly through the folded layers, you would create a passage, a wormhole. Suddenly, a journey that might have taken thousands of light years could be traversed in a fraction of the time. This is the fundamental promise of a wormhole, not traveling faster than light, but fundamentally redefining the distance you need to travel. Theoretically, a wormhole possesses two mouths in different regions of spacetime, potentially separated by immense distances or even different moments in time. These mouths are connected by a throat. The journey would involve entering one mouth, passing through this throat, and emerging from the other. It's a tunnel, but not through rock or earth. It's a tunnel through the fourth dimension, through the very geometry of reality. However, the original Einstein-Rosen bridge came with a significant catch. Further analysis revealed that these theoretical tunnels were incredibly unstable. The throat of the wormhole would pinch off and collapse into a singularity so quickly that not even a single photon of light would have time to pass through. They were non-traversable. The bridge would form and vanish in an instant, making it useless for any practical purpose. The dream of interstellar travel through these cosmic subways seemed to die as soon as it was born. To hold a wormhole open, to make it a stable, traversable gateway, would require something far more exotic, something that defies our everyday understanding of physics. And so the wormhole remains one of the most tantalizing concepts in modern science, a beautiful mathematical possibility, a gateway to the stars that is, for now, locked. But the quest to unlock it continues, pushing the boundaries of our knowledge about the cosmos. Wormholes come from Einstein's theory of general relativity. The math suggests they are possible, but keeping them open is another challenge. They would likely collapse instantly unless stabilized by something exotic, matter with negative energy density. We call this exotic matter. Without it, a wormhole would be too unstable for travel. One of the most fascinating ideas is that wormholes might allow time travel. This isn't just science fiction. It's a possibility emerging directly from the mathematics of Einstein's general relativity. The theory describes how massive objects warp space-time, and a wormhole is the ultimate expression of that warping, a tunnel connecting two distant points. But what if those 2 points are not just separated by space, but also by time? The key lies in time dilation. If one end of a wormhole moves at near light speed or sits in a strong gravitational field, time would flow differently between the two ends. Imagine we create a traversable wormhole in the year 2050. We keep one mouth, Mouth A, stationary on Earth. The other, Mouth B, is placed on a starship and sent on a round trip at nearly the speed of light. For the crew, the journey might take only 5 years. But back on Earth, due to extreme time dilation, 500 years could have passed. When the ship returns, Mouth B is chronologically much younger than Mouth A. The year on Earth is now 2550, but for the ship, it's only 2055. The two mouths of the wormhole, now sitting side by side, have become a gateway through time. If you were to step into Mouth A on Earth in 2550, you would instantly emerge from Mouth B in 2055, traveling 495 years into the past. In theory, you could enter one side in the present and emerge from the other side in the past, or the future, simply by choosing which mouth to enter and when. But this incredible possibility crashes into a wall of paradoxes. The most famous is the grandfather paradox. What if a time traveler goes back and prevents their own grandparents from meeting? If they were never born, they could never have traveled back in the first place. This creates a logical contradiction that seems to tear at the fabric of causality, the fundamental principle that cause must always precede effect. How can the universe resolve such a blatant violation of its own rules? Several fascinating solutions have been proposed. The Novikov self-consistency principle suggests the universe forbids paradoxes. You can travel to the past, but you cannot change it. Any action you take was always part of history, contributing to the timeline you came from. Alternatively, Stephen Hawking's chronology protection conjecture argues that the laws of physics themselves prevent time travel. A feedback loop of vacuum fluctuations might build up at the entrance to the time-traveling wormhole, destroying it with a blast of energy the moment it becomes capable of violating causality. A final, mind-bending possibility is the many-worlds interpretation. In this view, traveling to the past doesn't change your history, but instead causes you to enter a new parallel universe, leaving your original timeline untouched. From Interstellar to Stargate and countless sci-fi novels, wormholes have captured our imagination. They serve as cosmic highways, connecting civilizations and making intergalactic travel possible. Science fiction brings to life what physics only hints at: bridges to the stars. But before we pack our bags for another galaxy, reality sets in. Creating or finding a wormhole requires energies far beyond our current technology. The exotic matter needed has never been observed in usable amounts. And even if wormholes exist, they may be microscopic or hidden deep in black holes impossible to access. Wormholes remain one of the greatest mysteries of physics. Born from the elegant mathematics of Einstein's general relativity, they are a prediction that pushes our understanding of the universe to its absolute limit. These theoretical bridges, connecting distant points in space-time, are a natural, if unproven, consequence of the very laws that govern gravity, stars, and galaxies. Yet despite their firm grounding in theory, not a single one has ever been observed. This profound gap between what the equations permit and what we can actually find is the central enigma that captivates and frustrates physicists. It's a cosmic riddle written in the language of mathematics, waiting for a solution. The chasm between theory and reality is vast, filled with colossal engineering and physics challenges. For a wormhole to be traversable, it must be propped open against the immense gravitational forces trying to crush it shut. This requires a substance with properties so strange, it defies conventional physics: exotic matter possessing negative energy density. While phenomena like the Casimir effect prove that negative energy can exist on a quantum scale, the amount needed to stabilize a human-sized wormhole is astronomical, far beyond anything we can currently conceive of producing. Furthermore, the intense radiation and tidal forces within the wormhole's throat could prove instantly lethal. The universe, it seems, has erected formidable barriers around its greatest shortcuts. But what if these barriers could be overcome? If we could one day harness the necessary physics, wormholes would represent the single greatest leap in human history. They may forever stay in the realm of theory, or one day become the gateway to the stars. Journeys that would take thousands of generations could be completed in weeks, days, or even moments. We could explore the surfaces of planets orbiting Proxima Centauri, witness the birth of stars in the Eagle Nebula firsthand, and establish outposts across the Milky Way. The promise is not just about travel, it's about transforming humanity into a truly interstellar species, ending our cosmic isolation forever. Until then, the very concept of wormholes serves a vital purpose. It reminds us that the universe is far stranger and more exciting than we can imagine. The quest to understand them is a continuation of the same fundamental human drive that pushed our ancestors across oceans and eventually to the moon. It forces us to ask profound questions not only about the cosmos, but about ourselves. If we held the keys to the galaxy, what would we do with them? Such power would come with immense ethical responsibilities, forcing us to mature as a species. Even if we never travel through one, the journey to understand them has already reshaped science, connecting the physics of the very large with the quantum world of the very small. The pursuit of this ultimate frontier pushes us to be bolder, more imaginative, and more curious. It is a testament to our refusal to accept that we are confined to our small corner of the cosmos. The wormhole is more than a destination. It is a symbol of our unyielding reach for the unknown. They are not just tunnels through space, they are tunnels through possibility itself.